Doing fine? Extremely thrilled about trigonometry, I see. All right, so let's move on to some new stuff. So we've defined all of the trig functions so far. Make sure we define them for all real numbers and not just for acute angles. We played around with their graphs and see what the kind of behavior of the different types of functions are. And now we're going to shift towards thinking about being able to solve equations involving trig functions. In order to be able to solve equations, of course, you usually think about trying to isolate an x value. To be able to isolate things, you have to undo whatever was done to start with, right? So for example, if you've got 3x equals 9, I've got to undo multiplication by 3. If you have an x squared equals 9, I need to take the square root of both sides and get plus or minus 3, right? I need to be able to undo those types of functions. So if we want to solve an equation involving a trig function, I need to have a way to undo whatever that trig function did. The idea of undoing things is the idea of taking an inverse. So that's what we're going to talk about today, is being able to undo these trig functions, and we'll talk about taking the inverse trig functions. In this take on quiz too. All right. So we need to talk a little bit about when we can undo functions. Or undo functions and find inverse functions. I should be more technical and say find inverses that are also functions. Okay. And I'll talk about what I mean by that here in a minute. To be able to undo things, though, we need to have a property that's referred to as one-to-one. Before I write down the actual property, let's think about what I mean. So I mentioned earlier that if you want to solve the equation 3x equals 9, we undo multiplication by 3 by dividing by 3, right? Or multiplying both sides by 1/3, right? You get x equals 3. Something you've done for a long time, right? Okay. And notice that when I do that, I only get one possibility, right? There's only one way to undo multiplication by 3, and that is to divide by 3, right? However, the other equation I came up with that I mentioned a minute ago was the x squared equals 9. When I talk about undoing squaring, I usually think about doing the square root of both sides and get x equals 3. Unfortunately, that's not quite the right answer for that equation. And the reason is 3 the only thing that we can square to give us 9? No. What else can we square? Negative 3, right? So in particular, if I put in 3, or if I put in negative 3 for x into the squaring function, I get the same thing out, right? So that's an example of a function that is not one-to-one. I have two inputs that give me the same output, okay? So when we solve an equation like that, we typically think of like, okay, I know 3 is kind of a principal answer, but there's another one that I have to go find, which is also a possibility. And we're going to see the same issues pop up when we solve equations with trig functions, okay? Not today. We're just going to introduce what inverses are. But know that we have issues with the squaring function. We've already seen that before in a college algebra class or an algebra 2 class or whenever you solve undoing squaring, okay? Pardon me. Oh, it's making me cough today. But know that when we have functions that are not one-to-one, when multiple inputs give the same output, solving equations becomes a little bit harder, and we have to do some extra work. For squaring and doing square roots, there's not that much extra work. I have to do a plus or a minus, right? So we'll have to do similar types of things for trig functions, okay? Because you already know that trig functions definitely are not one-to-one, because, for example, if I plug in any multiple of pi into sine, what do I always get? If I plug in any multiple of pi into sine, there's a graph of it on the screen, or your paper. It gets 0 out, right? That's where it crosses the x-axis, isn't it? Okay. So no, I notice already that sine is not 1 to 1 because if we plug in 0 or pi or 2 pi or 3 pi or negative pi, I get 0 every single time. So going over to our definition of 1 to 1, it's 1 to 1 if distinct inputs yield distinct outputs. Now, that's not a very mathematical way to say something, right? That's in words. Usually, mathematicians like to change words into symbols for lots of different reasons, one of which is because we're inherently lazy. We don't like to write out words. Okay. But generally speaking, we want to have the same language, make sure we're all on the same page. It also helps us with logic issues if there are any. We don't want to worry about people interpreting meanings of words differently. Okay. So let's change this into symbols. This says that in symbols, distinct inputs would mean that I have x1 not equal to x2. That's what distinct inputs would mean, right? Different inputs, different outputs then would be f of x1 is not equal to f of x2. Okay? So if I write it as an if-then statement, we would say that if x1 is not equal to x2, then f of x1 is not equal to x2. That is a more algebraic definition for 1 to 1. Okay? I put different things in, I necessarily got different things out. A lot of times you will see this written kind of in the reverse order. What I mean by that is we do what's referred to logically as the contrapositive. It means flip the statement around and negate them. That's what contrapositive means. Okay. So what I mean by that is that another way to say this is that you could say if f of x1 equals f of x2, then x1 equals x2. Notice I flipped the statement around and made them positive statements, right, rather than negative statements. Thinking about it in words again, if you got the same thing out, you must have plugged the same thing in. The reverse idea of what we were thinking. In general, though, distinct inputs give you distinct outputs is 1 to 1. All right, so let's go back again to why x squared isn't 1 to 1, and let's think about it graphically. What's the graph of y equals x squared? It's a parabola. A parabola just means it's like a U shape, right? That way. That's what y equals x squared looks like. We said a minute ago that if we plug in 3 or plug in -3, we get out 9, right? Either way, we get this point here, this point here. Notice that those 2 points, I didn't draw that to scale by any stretch of the imagination. Doing it for illustration purposes here. Notice that those 2 dots that I just put on the graph have the exact same y coordinate, or the same height above the x-axis, right? If I connected those 2 with a line, what kind of line would I get? If they're at the same y value, what kind of a line would I get if I connect them? Horizontal, right? It'd be a flat line, right? Okay. Notice that horizontal line crosses the graph at 2 points. That would mean exactly the same thing as what we said up here, right? If I have a horizontal line that crosses at 2 points, then I find 2 inputs that have the exact same output. Okay. So graphically, we can determine if a function is 1 to 1 using what's referred to as the horizontal line test. And that horizontal line test says that a function is 1 to 1 if and only if every horizontal line crosses the graph of the function at most once. That's what the horizontal line test means. You also probably remember the vertical line test. That tells you whether or not a graph represents a function, right? Okay. Horizontal line test tells you if you're given a function, is it a one-to-one function? Okay. Now, why do we care about one-to-one functions? Probably a good idea to ask that. So, remembering your stuff that you learned with inverse functions, I'll do this off to the side again. Remember the stuff that you learned with inverse functions. Let me just draw the first, whoops. That first equation that I tried to solve before was 3x equals 9. So let's consider the graph of y equals 3x. The function that undoes y equals 3x would be the function y equals 1/3 x, right? This function is take the input and multiply by 3. To undo that, you would want to take the input and multiply by 1/3, right? So if I look at what the graph then of the inverse would look like, I'm basically doing this as a review because we need to do the same kind of stuff here in a minute. So if you don't want to write this particular stuff down, that's okay, because this should be a review of inverse functions. Okay. So the graph of y equals 1/3 of x looks like this, of course, right? Hopefully that looks familiar, right? Smaller slope, makes it flatter. But we should see a mirror image idea, right? Remember that inverses interchange your roles of x and y. Inputs become outputs, outputs become inputs, right? So you should see some symmetry here. And in fact, that symmetry is about the line y equals x. I'll put that here in a different color. Notice that if I take my y equals 3x line and flip it about the line y equals x, I get my y equals 1/3 x line. That kind of makes sense if you think about interchanging x's and y's and think about your slope. Slope is rise over run, change in y over change in x. If you flip the roles of x and y, you get change in x over change in y, and reciprocate the slope. Right? So it makes sense if you think about it that way. But in general, to get a graph of y, the inverse function, you do a reflection about the line y equals x. Y's become x's, x's become y's. Inputs become outputs, outputs become inputs. Okay. So let's think about what goes wrong when you do that with the squaring function, y equals x squared. What goes wrong? And this is why I want to illustrate why we care about one-to-one functions. Here's y equals x squared, right? If you reflect that about the line y equals x again, notice that your graph, instead of having a parabola that opens, can't get it to go. Thank you. Again, instead of getting a parabola that opens up, it's going to open to the right. This is the parabola x equals y squared. That flips x's and y's. Does this red graph that I just drew pass the vertical line test? No. So the inverse of my squaring function is not a function. Right? Not a function. So that's what happens. When you have functions that are not one-to-one, their inverses are not functions. That's why we care about one-to-one functions. Okay? Overall, their inverses are not functions. So what did we do to handle this when we undid the squaring function, because certainly you undo the squaring function when you take square roots, right? What did you do to undo the squaring function? Well, the idea was that we really only looked at this part that I'm coloring in red. Because when I only look at that part when I color in red and ignore the left-hand side, when I do that, I take the inverse and it stops, right? And I get y equals square root of x. So how do we handle that? We looked at one piece of the graph that is 1 to 1 and took the inverse of that instead. And then if we needed another solution, we went and looked for the negative, right? That was how we did the plus or minus idea. Okay. So we call this restricting the domain. And this is exactly what we're going to need to do for the trig functions, because they're also very, very much not 1 to 1. Okay. So let's go over to our y equals sine of x graph. Okay. Looking at this particular graph, this function is definitely not 1 to 1, right? This function, y equals sine of x, is not 1 to 1. At all, right? We have multiple inputs. A minute ago, I said that, for example, oops, good grief. Writing apparently is a challenge today. For example, sine of any multiple of pi is equal to 0, right? So we have multiple inputs that give you the same output. So it's not 1 to 1. That's what it means to be not 1 to 1, right? I got several things that I can plug in, and it gives me the same output. So if I want to start talking about inverse trig functions, I've got to do something similar to what we did with y equals x squared. We need to cut down where we look. Okay? I can't look over all the entire sine function. In particular, if you reflect the sine function about the line y equals x, you get a sine function that goes along, or a sine graph that goes along the y-axis rather than the x-axis. There we go. Like that. All right. So let's talk about what we mean by restricting the domain. So that's on the next page here. Before we discuss this restricting the domain with the sine function, let's talk a little bit about why we restricted the domain with the y equals x squared. Again, there's y equals x squared, right? Okay. We need to cut the graph down so that we have a one-to-one function, right? I need a one-to-one function to be able to talk about inverse functions. It has to be one-to-one if I want to talk about an inverse being a function, okay? So I want to cut this down so I see a one-to-one piece. Well, there's lots of ways to do it, right? I could cut the graph from here to here. That's 1 to 1 on that piece, right? If I ignore everything else and just go between those two small little red lines I put, that's 1 to 1, right? I could make it a little bigger. I could go from here to here on the left hand or the right hand side, right? But none of those are exceptionally useful because I want to try to undo the squaring function. Undoing, I mean change inputs to outputs and outputs to inputs. Well, what are your possible outputs for the squaring function? When you square something, what do you always get? Positive, or I could also get 0, right? I could get 0. But certainly, if I square something, I can get anything from 0 off to infinity, right? Well, if that's my possible output and I want to change it to an input, I want to make sure that I can plug in anything from 0 to infinity, right? So that's what's telling me how I want to restrict this. I want to restrict it not to a small interval, but I want to make my restriction, if I can get that last little bit off of there, I want to make my restriction work so that I take up the entire range, right? I want to take up the entire range because I want to change my outputs to inputs. I want to be able to undo as much as possible, right? If I restrict too small, I can't undo everything that I can possibly get out. Does that make sense? I want to make sure that my range is entirely taken up. Well, notice for the squaring function, you have two options, right? I could do the right-hand side, and that'll take up the entire range. Or you could do the left-hand side and take up the entire range. Right? Those are the kind of the two options for the squaring function, right? We agree? We literally choose the right-hand side when we define the square root function. The left-hand side is the negative of the square root function. Okay? But we literally choose that to be what we even refer to as the principal square root. So when you write the symbol, you know you're doing the positive square root. If you want the negative, you literally have to put the negative sign in front of it. That's what we mean by a principal square root. When you do a cube root, you're also doing a principal cube root, by the way. There's two other cube roots, they both just happen to be complex. So you stay off of those. When you do a cube root in a real number, you get a real number. But there are two other ones that happen to be complex. We'll talk about that at the end of the semester. Be fun stuff. We'll enjoy it. Okay. One of us will enjoy it. See if anybody else doing it. Okay. All right. In any event, that's what we mean by restricting the domain for the squaring function. Okay. Looking at the sine function, the squaring function only had two choices. Looking at the sine function, I got a crap ton of choices, right? But I want to keep two things in mind. The first thing is I want the restriction to be 1-to-1. So the restriction of the domain results in a 1-to-1 graph, a 1-to-1 function, I should say. It's absolutely pointless to restrict the sine function on the interval from 0 to pi. Why is it pointless to restrict the sine function from 0 to pi? Is that 1-to-1? No. Right? The sine function doesn't pass the horizontal line test on that interval. Right? If it's not 1-to-1, it doesn't have an inverse function, which is the whole point of this exercise, is to find inverse functions. Right? So my restriction needs to result in a 1-to-1 function. Okay? Now I mentioned that up there when I did the squaring function. There's lots of little bitty pieces that you can cut into and make a 1-to-1 function. I can do the same thing here, right? I could cut this little bitty piece here, or this little bitty piece up here, or way over here, right? But what I want to make sure is I want to undo absolutely everything that I possibly can, right? That's why when we looked at the parabola, we did the right-hand side or the left-hand side, right? Because that takes up my entire range. I want to do the same thing for the sine function. What is the range for the sine function? Negative 1-to-1, right? So we want to, the restriction, encompasses the entire range, which is negative 1-to-1. Okay. We want to make sure we have both of those. I want a restriction that makes a 1-to-1 function because I want my inverse to be a function. I want my restriction to take up my entire range so that I can undo any output between negative 1 and 1. I want both of those things to happen. Okay? But again, you got lots of choices, right? the squaring function, we only had two choices that did that, right? We had left-hand side and right-hand side. The sine function, I got lots of choices that I could do one-to-one and take up the entire range, right? I could go here to there, I could go there to there, there to there, there to there, there to there, right? I got all sorts of choices I can make, right? I can go from low point to high point or high point to low point infinitely many times. I got lots of choices I can do. So again, this is a choice, okay? We choose to restrict to a particular one, okay? We're going to choose to restrict from negative pi over 2 to pi over 2. It's a choice, okay? We're going to choose that interval, okay? The reason why I'm making a big deal out of that, besides the point that we need to make a big deal out of it, one of the reasons why I'm making a big deal out of it is that we'll talk about inverse sine, we'll talk about inverse cosine, we'll talk about inverse tangent quite a bit. There's three other trig functions, right? Inverse tangent, or inverse cotangent, inverse secant, inverse cosecant. It's difficult because, at least for inverse secant and cosecant, people can't really decide where to restrict the domain to. I've seen at least three different options from the different textbooks. This is why we're not going to talk about those particular ones for the research. Okay? But this is why I make a big deal out of it. Where you restrict is a choice. Okay? It's not just something that comes up mathematically naturally. We are making a choice where to pick this. Okay? Now, one of the things that this choice does is, remember, we're changing inputs to outputs, right? And outputs to inputs. So now we're getting, if you think about sine of an angle equals a number, we're going to do inverse sine of a number gives us an angle, okay? Where do those angles have to end up between? They have to end up between negative pi over 2 and pi over 2, or they end up in quadrant 1 or 4. Okay? That's an important thing to recognize. So when we do the inverse trig functions, what quadrants they end up in, and what other quadrants you may have to go look for an answer. We're going to develop that as we go along, okay? But just realize that that is a consequence of this restriction. Okay. All right, so let's talk about the graph of the inverse sine function. Okay, I'm going to put the original. You don't have to draw the original graph on here if you don't want to. To start with, I'm going to put it on here just to help. Well, I'm already in black. The original would go be a 1. Negative pi over 2 is somewhere over here. Pi over 2 is somewhere over here. And it goes, oh, negative 1's about here. It would go something like that, roughly. That's the original graph. It's flat, but that's what the original graph would look like. Remember, again, to get the inverse graph, we flip along y equals x, right? So the point, this is the point pi over 2, 1. That becomes the point 1 pi over 2. So it's going to be, let me put it in a different color so you can see a different color here. It'll be up here, right? This is the point negative pi over 2, negative 1. So it would flip over here. And you'll get something that goes up this way and like that. Again, it gets flipped. So this would be your graph of y equals inverse sine of x. I'm not sure the original graph helped at all. But again, it gets flip-flopped, right? So your line y equals x would be right in between those things. Oh, no, it doesn't go that way. Sorry. Let's try that again. It goes this way. Oh, that was bad. One more time. Sorry. It goes that way. How do I know it goes that way? Instead of the way that I originally drew it was wrong. How do I know it goes that way? would you say that this part of the graph is very steep or very flat right here? Flat, right? Matter of fact, it bottoms out, doesn't it? Do you agree? So if I take something very flat and I flip it around the line y equals x, very flat becomes what? Steep. Very steep, right? If I flip, in particular, if I flip a horizontal line above the line y equals x, I get a vertical one, don't I? So instead of being very flat here, it should be very steep here. Right? And then likewise over here. It's flattened out over there. So it should look like this. In particular, if I were to continue this graph, I said this a little bit ago, if I were to continue this graph, you should see a sine curve on the y-axis instead of the x-axis, if you were to continue it, which would make it not a function, right? Okay. All right, anyway, let me erase that part because I don't care about that part. Anyway, that's what the graph looks like. Apologize for messing it up the first time. Stuff happens. Okay. All right. So let's think about domain and range. Remember, domain of the inverse is the range of the original. Range of the inverse is the domain of the original. Well, so let's do domain first. The domain of inverse sine is the range of sine. What's the range of sine again? Negative 1 to 1, right? So this will be negative 1 to 1 here. The range of the inverse is the domain of the original. Here's where the restriction comes in. What did we restrict to for the original sine? Negative pi over 2 to pi over 2, so that'll be the range of your sine function. Again, you cannot plug anything in for inverse sine that's not between negative 1 and 1. You cannot get anything out of inverse sine that's not between negative pi over 2 and pi over 2. Okay? All right. So let's see if we can develop a couple of the other inverse trig functions, then we'll do some examples probably on Friday. Let's flip to tangent. Is tangent 1 to 1? No. Okay? So same principles. We need to restrict to an interval that is 1 to 1. And we also want to keep in mind the same principles that we talked about for inverse sine. Not only do we want to be 1 to 1, we want to make sure that it takes up the entire range of the tangent function. What is the range of your tangent function? Negative infinity to infinity, right? So basically I want to pick one of those intervals where I see one of those S-shaped kind of things, right? Little snake things, right? Okay? Again, it's a choice, right? But I'd like my choice to kind of try to match my previous choices. I don't want to, my brain is small. I don't want to remember more things than I need to. Okay? We restricted sine negative pi over 2 to pi over 2. Can you use the same restriction here? Yeah, it's in between those two asymptotes, right? Yeah, it just can't be that you can't do the exact values, you're exactly right. But that same interval will work, right? As long as I don't include the endpoints. Okay. So same idea. In this one, we will restrict the interval negative pi over 2 to pi over 2. We can't include the endpoints because we have asymptotes. But again, trying to minimize the number of things you have to try to memorize, restrict it to the same area, right? If you can, keep it simple. Okay. All right, let's think about what the graph looks like now. Again, here we have a vertical asymptote. Here we have a vertical asymptote. A minute ago, I just said, if I flip, pardon me, if we flip a vertical line around the line y equals x, what kind of line do we get? If I take a vertical line and flip it along that diagonal, we get a horizontal line, right? So when we flip, we get horizontal asymptotes. The equation x equals pi over 2, when you reverse roles of x and y, x equals pi over 2 becomes y equals pi over 2. That's a horizontal line, right? And then when we flip our graph, we'll get something that looks like so. So there's our graph for inverse tangent. This probably looks different than any other graph that you've seen before. The reason why I say that is because this function has two horizontal asymptotes. When you've dealt with rational functions before, when you have something with x's on top and something with x's on bottom, usually you get one horizontal asymptote, right? This function has two. That's the maximum number of horizontal asymptotes you can have, by the way. You can't have more than two. For the horizontal asymptote, you have to either get really, really big in the positive direction or really, really big in the negative direction. Those are the only two directions you can go for x's. You can have infinitely many vertical asymptotes. Tangent does. Cotangent does. Secant does. Cosecant does. You can have infinitely many verticals, but you can only have at most two horizontals. But like I said, this is might be the first function that you've seen that has two, unless you've dealt with algebraic functions in your algebra classes before, which I bet you haven't. So, okay. Anyway, this is what the graph looks like. So let's do domain and range. Remember, domain of the inverse is range of the original. What was the range of the original that we got? What's the range of the tangent? Negative infinity to infinity. So the domain of your inverse tangent is negative infinity to infinity. You can plug anything in you want. But what has to come out? The range of the tangent is the domain of the original, and we were restricted to what? And pi over 2, and those are not included, right? We see those with the asymptotes there. Questions on that? Yes. You can write, yeah. We usually like to write things in interval notation, so that's why we do it that way. But you can say, yeah, in this case, it's all real numbers. That's right. All right. Inverse trig function number 3. Like I said, we're not going to go do cotangent, secant, or cosecant. So it's just these three are the ones we're interested in. All right, so definitely not one-to-one. Still want to use our same principles for restrictions, right? We want to make sure that we have a one-to-one function and it takes up the entire range. Can we use the same restriction that we did for the previous two? Can we use negative pi over 2 to pi over 2? No. Negative pi over 2 to pi over 2, get something that is not one-to-one and doesn't take up the entire range. It violates both of our principles we're trying to do, right? Okay. So we have to move our choice. What do you think we might choose? If we want to make it one-to-one and take up the entire range, what interval do you think we might use? Instead, 0 to pi, that works. And that's exactly what we do use. We go from 0 to pi. That'll work, right? There's a whole bunch of other ones that do, but 0 to pi definitely works. One of the reasons why we choose 0 to pi is because there is at least some overlap with the other two, right? If I try to do a different interval, I won't have an overlap with the other two. But in this case, we're going to restrict to 0 to pi instead. Pardon me. I didn't make a very good graph on here. All right. Because it should go off to pi. All right. So, in any event, here is the point 0, 1, here's the point, pi negative 1, right? We should flip-flop those things, correct? So 0, 1 becomes 1, 0. I didn't make a very good graph on this one. I should have changed my scale. The other point, instead of pi negative 1, should be negative 1 pi. It should be up here. And then again, this is the point, pi over 2, 0. So we should be at 0 pi over 2. It's flat here. So it should be steep here. Then go this way and be steep over here again. So that would be your y equals inverse cosine. So I apologize for not making the scale a little bit better. Again, this is just a piece of what x equals cosine y would look like. It should be the cosine graph that goes along the y-axis instead of the x. Same graph, just basically sideways. All right. So let's fill out what the domain and the range would be. What's the domain here? Negative 1 to 1 again. And the range is going to be 0 to pi. Good. Pardon me. Before we go on, one thing I do want to mention is about the notation. Remember when we put that little negative 1 in there? Next to the function, that means inverse, right? It does not mean flip it upside down. Okay? So be careful with that. This means inverse cosine. Does not mean that. If I want to flip cosine upside down with a negative exponent, I would write it with parentheses around it and put a negative 1 power. But I would never do that anyway, because what is the reciprocal of cosine? Secant, right? So this does not mean take the reciprocal. It means do the inverse function. We already have a notation for take the reciprocal. Okay? Another notation you might see in other books or other resources, if instead of a little superscripted negative 1, you see ARC in front of it, that also means inverse cosine or arc cosine. Sometimes is what people will say. That's another notation. Or even more abbreviating, then I just put an A in front of it. I will use this one all the time. Okay. The danger of that is it makes you think of a negative exponent, but it's not. It's a notation for the inverse. Okay. So be careful with that is what I'm saying. All right. Almost, well, we'll probably do some actual numbers next time, but let's talk about these properties, fill those in, and then we'll do examples next time. Properties of inverse functions. Well, the whole point of doing inverses is to undo what the original did. Right? If I multiply by 3 and then divide by 3, I get back to where I started. If I square and then take the square root, I should get back to where I started. Right? All of those things on the left-hand side of the equations are, I take the sine and then undo it, or I take the cosine and then I undo it, or I take the inverse cosine and then I undo it, right? So in all of those cases, oops, there's a typo. There should be an X in there. It should be cosine of X. Sorry about that. But in all of those cases, we're applying a function and then applying the inverse function. So where should I end up? If I apply a function to x and then apply the inverse function to that output, I should end up back at x again, right? I should end up where I started, right? So all of these answers should be x. Every single one of those should be x because I'm applying a function and then applying the inverse. That's our goal, right? That's the whole goal of inverse function, is to undo what you did, right? Okay. However, there must be a however if I've got ifs there along the side, right? Let's think about why there's a however that pops up. What's that equal to? 2. What's that equal to? It's also 2. Didn't get back to where I started, right? What happened? Remember how we create the square root function. We first restrict to what interval? 0 to infinity. Is that in that interval? No. Okay. So this composing function with inverse only gets you back to where you started is if the input's in the right spot. Okay? So let's think about the first one. I'm going to take the sign and then do the inverse sign, right? This has to be in my domain restriction, right? So your x here has to be between negative pi over 2 and pi over 2. That x has to be in the domain of sine. But what I mean by that is not just the domain of sine, since that's all real numbers. It has to be in the domain restriction for sine for it to work. Okay? Likewise, if I jump down to the third one, this one has to be between 0 and pi. This one has to be between negative pi over 2 and pi over 2. The x that you have has to go into the original function. We restricted the domains of all the original functions, so my x has to satisfy that restriction in order for that to work. That's what that says. Okay. Going the other way, I need to make sure that my x can go into the inverse sine function to start with. Right? So it has to be in the range of the original. So my x here has to be between negative 1 and 1. It has to be in the range of the original, right? I cannot take the inverse sine of something that's not between negative 1 and 1. Same thing for cosine. However, for inverse tangent, it's just fine. It works for all real numbers. Or any real hashtag. Sorry, when I grew up, that was a number sign. Or a pound sign. Now it's a hashtag. Things change. Anyway, is that okay? All right. So we'll practice these problems next time. We'll do some examples. I know it's kind of heavy on the concepts today, but I want to make sure that I reinforce where everything is coming from. It's a big deal as far as that goes. In particular, it's a big deal when we start solving equations. Your take-home quiz is due on Friday that I gave you at the beginning of class. Pardon me. Otherwise, we'll finish this packet up on Friday. Have a good one.